Hi, welcome back to Discovering Patterns in the Microbiome. Today we're going to talk more about statistical testing, but some more advanced aspects. So in the previous video, we covered some of the common parametric tests that have a normal distribution underlying them. So a t-test, which is used for comparing two groups, ANOVA when you have more than two, correlation when you're comparing your outcome to a continuous variable, and then linear regression, which is similar to correlation, but you can also control for confounding variables. And we noted that these are all normal distributions, and we can often do better. There are cases where linear models are not always appropriate. We're going to see some of that today in this video. And then, so we're instead going to use generalized linear models. This is where the underlying assumptions are different about what the distributions are. And then we'll also talk about nonparametric tests. And finally, one thing that's going to come up is controlling for multiple tests. So when we have a hypothesis about a single outcome, we can just test it. We get the p-value and we're done. But in the microbiome, because it's so high dimensional, we often have many features that we're testing. For example, you could test every genus that was seen in the global gut study for whether it's differentiated according to country. And when you do that, let's say there are 100 genera that you test. When you do that, some of them are going to come out looking significant just by chance. So in fact, on average, if you have 100 tests, you should have 5 of them with a p-value of less than 0.05, because p-values are supposed to be uniformly distributed. So we can fix that using a number of different methods. The common way for genetic testing is to use Bonferroni, which is where you basically multiply the p-value by the number of tests you're doing. So if or you divide your threshold by the number of tests you're doing. So for the Bonferroni correction, if you're doing 100 tests, then instead of using a cutoff of 0.05 for your p-value, you'd use a cutoff of 0.0005. This is a more strict approach. It's controlling the expected number, it's controlling the expected probability of having one or more errors. False positives. The more common approach in microbiome analysis is to use false discovery rate, and people have been using this in gene expression tests too for a while. False discovery rate is more lenient because it's controlling the expected number of false positives, not the probability of having at least one false positive, but the expected number of false positives. So people will often use a higher false discovery rate cutoff, like say 0.1 or even 0.2. And what this means is, so let's say you use a false discovery cutoff of 0.2, that means that you're expecting that 20% of the hits that you're calling are false positives. So we're going to see that. And then for the generalized linear models, these are ones that don't have to rely on a normal distribution. We're going to use the negative binomial. And negative binomial is it's a very flexible distribution. The interpretation of it is that it's the number of successes you'd have if you're repeating some random event and that could have a success or failure. It's the number of successes you'd have before you have a given number of failures. So if, for example, if you're rolling a 6-sided die and you're trying to get a 1, it would be how many 1s do you expect to get on average before you've seen a particular number of non-1s? Or, for example, 5, how many 1s will you get before you've seen 5 rolls that weren't a 1? That's how it can be explained. But it has a nice property that, depending on the parameters of the distribution, it can look kind of like this, where you have, this is like a lot of microbiome features where you have a few people who have, you have a lot of people with very little amount of that bug, and then a few people with a medium amount of that bug, and then occasionally there are a couple people, just a handful of people that have a lot of that bug. So you can get that type of distribution. But as you change the parameters, this distribution can actually morph out to look more like a normal distribution. So it's a very flexible distribution. And so you can see an animation here as we're changing this parameter R, it's becoming more and more like a normal distribution. So now we're going to do a little demo of using this method and also multiple hypothesis testing, correction, and the nonparametric approach. The nice thing is that negative binomial was already implemented it was implemented previously for doing gene expression tests in the EDGE-R package. And so you can actually use this exact same model on the microbiome. Here we are at the course code browser. We're going to go to statistical analysis. And we are working in the code repo, the course repo, in the global gut with 66 adults directory. So if we go to the repo, we're in data, global gut, 66 adults. I want to run these tests on the genus level. So we have already run this summarized taxa, and we've converted the output to the correct format of the older format of biome tables so that we can load it into R using the biome package. Last time we ran some statistical tests here where we did basic association testing with the correlation, that's Pearson's correlation. We fit a linear model, and if you'll recall, we fit a model, so we wanted to find out if the abundance of Prevotella, the genus Prevotella, was related to how old someone is. So we did a simple linear model, and it turned out that it wasn't quite significant. The p-value was 0.053. Then we did a little test to see if the linear regression was appropriate. So one of the main assumptions of linear regression is that the residuals, which is how much above and below the regression line the errors are, should be normally distributed. We made this little QQ plot, which looked okay, and we ran a Kolmogorov-Smirnov test, which gave us a p-value telling us that Prevotella did not look significantly different from a normal distribution after regressing on age. So what this means is it's okay to use a linear test probably for doing that test. We also followed up by controlling for confounders because age and country might be confounded, and so we used the same linear model to remove the effect of confounder. Prevotella became significant. Now, when we do these tests, we're not usually testing just one genus. We often want to test all of the genera, or all of the phyla, or all of the OTUs. You can do that with a loop that I've shown here. So that's this for loop. If you're not a computer programmer, you can either go read up about for loops, or you can cut and paste this into a text file and save it, and then it's easy to ask R to run that text file. Or you can just put it all on one line, and I gave you the one-liner version here, and you can cut and paste that into the command line. But the point is, what we're doing is we're going to walk through every column of the genus table and run the exact same linear test where we're asking, is that genus correlated with age when we're controlling for a function? So you can see I is going to be the values of the numbers of the columns in genus, so 1, then 2, then 3, and so on. We're going to get the fitted linear model from testing a particular genus. So here's where we're getting one column out against age while controlling for country. Then this is where we extract the p-value. And notice we're storing the p-value in this p-vals vector. And I've done a little work ahead of time to set up the p-vals vector so that it's the right length, and I made sure that it's named, so each entry has the same name as the columns of the genus table. And when you run this code, what you get is, so here we're printing out just the 10 smallest p-values. You get a list of all the p-values, and looks pretty good. Here, this whatever this is, WPS2 is highly different between the countries. There's Prevotella, highly different. I mean, sorry, not countries, highly associated with age. Prevotella, Verruca microbia, Christensenolaceae, and so on. But the question is, are these actually significant, or are they just happening by chance because we did so many tests? Here's the one-liner version. Here's a different one-liner version. You can just cut and paste this onto the command line. So this is the first thing we're going to do is when you have multiple hypothesis tests, it's very easy to correct all of the p-values in R. And we can do that with this p.adjust function. So you just run this function on the p-values and tell it we're going to use FDR. So this is the false discovery rate. And what we get out are often called Q values. So Q values are corrected p-values. Let's sort those and take a look. And here's what we get. Okay, Prevotella, that weird bug, the Verruca microbia, a couple of others, Christensenolaceae. These are coming in at a maybe okay FDR rate. So you might be able to use 0.2 as a cutoff for your false discovery rate. However, if you only have like 1 or 2 or 3 hits, then it's not quite as legit. Like let's say you run this test and you find out that there are 20 genera that have a Q value of 0.2 or below. Then you could say, okay, we're just going to call these all hits, knowing that about 20% of them are wrong, so about 4 of them are wrong. But when you only have 3 that are below 0.2, it just gets a little sketchy. So you could probably publish this, but you really would be hoping for a lower Q value, like 0.05, or lots of Q values below a certain threshold. Now, so that was the correction for multiple hypothesis testing, and we're going to use that in the other tests that we run now. So what I want to do is we're going to go back to the linear regression we just did. So we ran a linear regression on every column in the genus table. This was every different genus. We already checked one of them, which was Prevotella, to see if the residuals were normally distributed, and they looked okay. But we don't know about the rest of them. So we're going to run another for loop here. Okay, we get lots of warnings from this test. This is the Kolmogorov-Smirnov test. Again, same as before. And we're going to do a similar loop, just like we did on the last one. So we're going to walk through every column. We're going to fit a linear model, exactly the same as before. But this time we're going to run the Kolmogorov-Smirnov test on the residuals of that column, and then store that in another vector here that's called ks.pvals. And then at the end, so it's gonna run all of those tests. It prints this warning, which is really annoying and takes up a lot of space, but you can ignore it. and then now we've got a list of p-values for the test for normality. We can correct those because we did multiple hypothesis testing. So let's correct those the same way. P dot adjust false discovery rate. And now let's look at the first 10. So what are we hoping for here? We're hoping that none of these tests are significant. Because if none of them are significant, that means we can just stick with our linear regression and not have to do anything fancy. But if some of them are significantly non-normal, then we need to apply some other fancier model because the linear regression assumptions are being violated. And unfortunately, even after correcting for multiple hypothesis testing, these p-values are off the charts. So Bacteroidalis RF16 family is highly, highly significantly non-random when you look, non-normal when you look at the residuals after linear regression. And a whole bunch of others too. In fact, there are lots and lots of them that are not normally distributed. So sadly, we have to move on from linear regression, and we're going to use a generalized linear model. So here we're using the negative binomial that we discussed in the edgeR package. If you don't have edgeR, you can install it using these commands. And then it's a little tricky to use, so I've made a wrapper script that is in the course repo in the source directory. So you can see that online. If you go to the course repo on GitHub and look in source, there it is, wrap_edgeR.r, it's called. In R, when you have commands stored in a file and you want to load them in, you just say source and then the name of the file. So I'm going to source that R file, and now it's ready to go. So we're almost ready to run a negative binomial generalized linear regression on our data, but the negative binomial is based on counts. It's not based on relative abundances. So we need to go back to the summarize taxa command and generate absolute abundances. What normally comes out of it is the relative abundances. We need to have the raw counts. We saw this genus 2 times in this sample, this one 40 times in this sample, and so on. So, we're going to exit out of R. On the command line, we'll run summarize taxa, and it's exactly the same as before with -a. So that just says use relative abundances. And then in the output, we have to convert the output again to the old form of biome so that we can load it into R. And then we just load it in the same way as we did before, except here I'm going to store it in this genus.a. And the nice thing is, there's a little benefit here. So if we look at these absolute abundances, some samples may have more reads than others. And in fact, you can take the raw read counts off of your OTU picking before you rarefy the data and put those into the negative binomial. It knows how to deal with that. And that's a really nice advantage because you're not having to throw out data in the statistical tests by rarefying. So we've got the table now. It's got the actual counts, not just the relative abundances. And we're going to run the regression with covariates. And here's the function that I made. It's called glm.edgeR, so generalized linear model. We're going to pass in x, so that's the dependent variable, the independent variable. And here that's age. Then we're going to pass in y, capital Y, and usually capital letters are used to denote a matrix. So this is usually a matrix where it's the whole table of genera. And this function is going to run the test on each column of that and give me the results using the negative binomial regression. So, here's how we'll run it. And it does a few things. and we store the result in this variable called result, then the edgeR package has this command top tags, and you use that to make it print out the best hits for that analysis. So we call top tags on the result, and it's a little bit poorly formatted here because of the screen, but we can zoom out for a second and see it's got a list. So I passed in, when it asks how many tags you want to print, oh, sorry, no, for the first one, it's just going to print the top 10 tags. Okay, here's the top tags result, and it's going to give us the first 10 hits, or the best 10 hits for association of the genus with, a particular genus with H. So the best hit is Lactococcus, and we find, here's its small p-value, and we find when we look at the false discovery rate, that's the last column in these results, it has a value of 0.035. So we just squeaked by with a significant result for Lactococcus and Streptococcus when not controlling for country. We can use the exact same generalized linear model, but we can also control for covariates. So this is great. We're going to call the same function now. And we're going to pass in the covariates in addition. And here we just have one covariate we're interested in, which is country. So we're trying to control for the effects of country. We run that same command. We call it top tags on the result. And if we scroll down to wherever it has the FDR values, which is here, we see that unfortunately nothing came out. So Streptococcus is still at the top, but it's no longer significant when controlling for potential confounding effects of country. So, so the bottom line is here, when we ran the linear test, so straight up linear model, we did get significant, well, almost significant hits. They were like 0.13, a couple of them 0.13, 0.15. But we used the Kolmogorov-Smirnov test, and we found out that many of the genera were not normally distributed, or the residuals were not. So then we moved to the generalized linear model. A couple of things came up significant when we didn't control for confounding effects of country. Now that we've controlled for confounding effects of country, nothing is significant. So we've systematically backed off from our original assumptions to the point where we realized that there's not anything in these data that are significantly associated with age while controlling for the effects of country. However, we can run a different test where we're pretty sure something's going to be significant, and we will get some significant results. So now we're going to test whether bugs are different in different countries. First, we will do a test of whether or not certain bugs are more or less prevalent in the USA compared to the other countries. So we're going to use this equals command. So we're taking the country column from the mapping file, and we're comparing it to this string, GAZ, United States of America. Every entry that has that in it is going to get a true, and if it doesn't have that in it, it's going to get a false. And then that's going to be stored in this variable is USA. So we're going to go back to the same function, glm.edgeR. Now our independent variable is USA, and we're still testing all of the genera to find out if they're different, whether you're in the USA or not. And this time we're going to use age as the covariate. So age is the what we're trying to control for confounding effects of. So we let that run for a moment. We ask for the top tags out. And let's scroll down to where we get the FDR values. And yay, so now we've got lots of highly significant results. Rickenolaceae is very significantly associated with USA, even after correcting for multiple hypothesis tests. That's a p-value of 3.3 times 10 to the minus 38. And there are, I don't know, dozens of other significantly differentiated bugs. So the testing does work as long as you're not violating the assumptions, and there's actually a significant effect in your data. And so if you want to print out all of the results that come out of this, you can use n equals infinity. So that basically says, I don't care how many genera there are, just print the whole table of results. Then you can also save that table. Let's get to the bottom of this. If you want to write that table out to a file, you can do that with this write.table command and all these other things. And then you're going to have a tab delimited file, which you could open up in Excel. So for example, let's try doing that on my computer. So here's that file, open with Excel. And here's what the table looks like. So here are the different genera. In the next column, we have the log fold change. So that's the log fold change from non-USA to USA for that bug. There's the p-value, there's the false discovery rate. So you could put that in as a supplemental table in your paper. Here's how we could ask what fraction of genera were significantly associated with the USA. So I'm going to take the top tags function, pull the table out of the results, pull the false discovery rate column out. Then I'm going to compare each value in that column to 0.05, see if it's less than or equal to 0.05. So that's going to give me a list of true, false, true, true, false, and so on. Then I'm going to sum that, and the trues count as ones, and the falses are zeros, so the sum is 62. So there were 62 genera significantly associated with being in the USA, even after all those corrections. Great. So this was a nice test. This is a nice test that works well for microbiome data. If you have normally distributed data, you can just use the linear test. But if you run the Kolmogorov-Smirnov test and you find out that the residuals are not linear, normally distributed, then you should use the EdgeR test. The EdgeR tests are going to be a little more fragile. So if you have lots of covariates you're controlling for, it might throw some errors at some point. Whereas the straight up linear testing is very well vetted. It's been used for years and years. Now, last thing to discuss, nonparametric tests. Nonparametric tests are really nice because they don't have any distributional assumptions. So they can handle any possible distribution of data. They do this by acting more on only on the ranks of the values, like what order the values are in, not caring about the actual magnitudes of the values. And the first one we'll look at is it's sort of the equivalent to a t-test. So a t-test is when you've got two experimental groups and you want to see if a genus is different between the two of them. So the nonparametric version is called the Mann-Whitney-U test, sometimes called the Wilcoxon signed rank test or the Wilcoxon rank sum test. There are subtle differences between these, but they're kind of interchangeable. And so in R, we can run this. Wilcox.test looks just like a linear test or the t-test. So Prevotella tilde is USA. And here's what we get. Yes, Prevotella is significantly different between non-USA and USA. There's the p-value, 7.7 times 10 to the minus 10. Here's how you would get the exact p-value out. You use $, p-dot value. If you have multiple categories, so not just USA, non-USA, but you want to do like USA, Malawi, Venezuela, and ask for bugs that are differentiated overall across those categories, this is kind of analogous to an ANOVA test. There is a non-parametric version, it's called Kruskal-Wallis. That's also in R. So you would run that with Kruskal.test. And here, instead of the independent variable being is.usa, it's just the whole country column, which has those 3 countries in it. And we find out that, yes, this bug is significantly differentiated across countries. And then finally, for continuous variables, you can use Spearman correlation. So I highly recommend using Spearman in the microbiome instead of Pearson correlation, because Spearman doesn't take into account the magnitudes, it only takes into account the rank. And so if you have big outliers, it's not going to affect the correlation. So here we would run core.test. We're correlating Prevotella with age. We tell it to use the Spearman method. And then here's the result we get. So yes, Prevotella is significantly correlated with age with a p-value of 0.03. And here's the correlation, minus 0.26. So it looks like as you get older, Prevotella goes down. Although, keep in mind, we didn't control for potential confounding effects of what country you're from. And when we do that, that changes the results. In summary, when we use linear regression tests and they do not produce normally distributed residuals, we need to switch to something else. A great alternative is generalized linear regression using a negative binomial model. And you can use the edgeR package in R. There's a little nice wrapper script that I made that's in the course repo. When you run all of these, when you run these tests on lots of columns in the genus table or phylum or OTU table, you need to correct for multiple hypothesis testing. I suggest doing that with false discovery rate. And then finally, if you don't need to control for confounders, nonparametric tests are a very nice alternative. They're very reliable, they're very safe, they don't have any assumptions about the underlying distribution, so nobody can complain about your p-values. But they have lower power than the parametric tests that we've talked about. And I showed you a few different non-parametric tests and what their equivalents are on the parametric side. But as I said, there's no good way to control for confounding variables for the non-parametric tests, so there are lots of cases where we can't actually use them. So that's all for the advanced statistical testing.